Well, I think that was fantastic, and I'm glad I asked it. I hope most listeners stay tuned. I mean, the ones that gave up at some point are not listening anymore.
Probably somewhere around the music analogies, I'm guessing.
I mean, maybe we should make the cold open. All right, now I'm going to say my inflammatory thing so that people will hang on until they...
And then they know it's coming, yeah.
Yeah, they'll know that it's... or maybe that's what we should... Maybe that's what we should do. We should always make the... Whenever we're not sure people will listen the whole thing, just put a fake cold open.
Isn't that what we do?
No, just put a fake one there so they're like, oh, when's it coming? And
then we guarantee they listen the entire time waiting for it.
Welcome to another episode of ArrayCast. I'm your host, Conor, and today with me, I've got three panelists. We're going to go around and do brief introductions and have a couple announcements, and then get to our topic today. We'll start with Bob, then go to Marshall, then go to Rich.
I'm Bob Therriault, and I am a J enthusiast, and I'm very enthusiastic about J.
I'm Marshall Lockbaum. I started programming in J, and I worked for Dialog for a while, and now I make the BQN language.
I'm Rich Park. I've never really programmed in J, but I'm an APL programmer and teacher and evangelist working for Dialog Limited.
And as mentioned before, my name is Conor. I am a polyglot programmer and a huge array enthusiast, and I have programmed a tiny bit doing toy things in J, so 3 out of 4 is not bad. I think we'll start with Rich, because Rich has, I think, 6 announcements, so we'll try and burn through all of those, and then we'll go to Bob for a final announcement.
I mean, in my defense, I can do plus reduction in J. I can do that. Okay. Yeah, I've got a load of announcements, APL related. So, firstly, the APL Problem Solving Competition 2023 is now live. You can go on contest.dialog.com or dialogAPLcompetition.com. We'll only put one of those in the show notes, make it less confusing. If you are a full-time student, you have the chance to win cash prize. I think the large one is $2,500 and invitation to Dialog 23 user meeting to come present your work. If you're not a student, you should still compete because you could win free ticket to the same user meeting. And it's always awesome to meet the competition winners. So you've got like half a year, I think. Deadline's on the website, so I won't say exactly what it is because I don't have it on the top of my mind, but I think it's sometime in July. Solve problems in APL and potentially win money, so that's cool. Also contest programming language competition related. The sort of website service called Catis, they do some like verification of programmers for various companies, but they also have like an online contest platform called OpenCatis. I think that's open.catis.com, I think. APL is now one of the programming languages you can use, Dialog APL, to solve the Catis problems. So they have instructions on how you handle the input and how you're supposed to return the results. But yeah, if you want to go try some automatically verified contest programming problems, then open.catis now has APL support, which is cool. On very short notice news for when this comes out, it'll be Wednesday after this comes out, I believe. APL Seeds 23, so just a few days left to register if you haven't already. A few talks aimed mainly at people who have either just started learning APL or maybe they don't know APL yet but they're interested, and then afterwards we'll have like an informal meetup over Zoom where you can come hang out and chat about APL and array language stuff. Links in the show notes for where to find information and register for that. We're halfway there. Okay, Linux format is, on the front covers, I think it says like the premier or number 1 open source software magazine in the UK. I mean, I remember that was one of the ones I would grab from the newsstand. When you go on those long car journeys, you have to stop at a service station to find Linux format. Linux format issue 300, which came out this month, has a 4-page, fairly extensive article on APL and array languages. So that was really cool to see, with some quotes from Morten Kronberg, Michael Wallace as well, who was a previous guest on here, I believe, talking a little bit about what he does and some other things.
AKA Tangent Storm.
That's right. There's also a new APL show episode, the podcast of me and Adam talking about APL and sort of notation as a tool of thought. It's a reaction video. I thought we'd go out on a limb, take a bit of a risk and do that. But it's about a really nice presentation someone did about notation and thought at the 2022 Software Engineers Conference in Australia. And lastly, there is a new one-off episode of APL Campfire, which is a sort of like history-focused APL show hosted by Adam. I should have looked this up before to see who it wasn't about, but if you go to apl.wiki...
It's Norman Thompson.
Norman Thompson. If you go to apl.wiki/campfire.
And Norman Thompson was one of the guys when I was doing my master's degree, one of the things in education for APL, Norman Thompson has done a whole ton of stuff in terms of education and working with groups and how to educate them in APL. Really interesting guy. And I missed it live, but I will pick it up on the bounce.
Yes, I also missed it live, if you can't tell. And I also intend to watch that this week. So, sorry for the long one there.
Round of applause. We got through it.
You made it through.
All right, Bob, over to you for your one announcement.
Well, my one announcement is the JWiki continues to be emergent. It's slowly coming around, but this last week, Ed Gottsman made a really neat presentation about information on a wiki and how to present it. So he's developed kind of a GUI that he calls it mapping. And it's a really interesting concept. Basically, you keep the entire map of the GUI up all the time. And then as you click on different areas, your information comes up on the other side of the screen. So that sounds, that's so simple. He's done it in a way that's really interesting. And because he presented at the meeting and because we do video of the meetings, I made a video of it and put it up on my YouTube site. So there'll be a link there as well. If you're into that sort of stuff, not so much to do with the array languages, although if you're interested in how these wikis work and maybe some of the tools that could be put towards them, my jaw was on the floor as I was watching it. Yeah, it was good.
Yeah, I saw it as well. It's pretty neat. And speaking of videos, you just remind me that I actually also made a YouTube video that I totally... Well, I mean, it should have been top of mind. What was it called? Why I Love BQN So Much, which I'm sure makes Marshall happy.
Yeah, I saw that was there. I have yet to watch it because it's just from yesterday.
Yeah, I made it sort of... It was a late decision at like 7 p.m. because I looked at some video. Anyways, is it the video that my YouTube subscribers want? No. Is it the YouTube video my YouTube subscribers get? Yes, because it's it's pretty. There's certain videos I make. It's like 100,000 plus views. And it's pretty. I know the formula to get that, and then those ones just are they're interesting, but not as interesting as the BQM ones. And APL ones. Anyways, link in the show notes. I'm pretty sure like the overlap of people listening to this and watching those videos is quite high. But if you happen to not know about that channel, and also I guess it's worth mentioning because the APL contest, Dialogue APL contest got mentioned. If you want little helper videos of like how to solve those problems, Adam, who's not here today, he has a sort of APL quest, I think it's called, which is basically going through the backlog of problems going back to whenever the contest started. So he has, I'm not sure if it's hundreds, but definitely tens of videos solving previous contest sort of phase one problems, so if you're not really sure how to get started, watching a few of those on that playlist would probably be super helpful. With all of that being said, today's topic, which is probably... Yeah, I mean, the listener always knows if they look at the title of the episode, is going to be on performance. And I think also measuring performance in specifically array languages. So I'm not sure where we want to start. I mean, I thought maybe...
I know.
Okay.
Actually, I think, and we brought this up in the pre-show, we should explain that Stephen is not here.
Oh, right, yeah.
Because he's hanging out with Arthur. Yeah. And that's... Honestly, he ditched us for Arthur, and that's all that needs to be said. Okay?
And therefore, we have no QKKDB representative. Yep.
You're not saying that gives us carte blanche to just crap all over Q and KDB
It does.
Well, we can do it. We just feel bad because Steven's not here if we do it. So we have to be civil. Yeah.
I mean, I'm not even sure if we can, which sort of brings us to, we were discussing this before. So we've brought this up on past episodes that there on and off has been a free downloadable Q and KDB plus executable that you can get from kx.com. But that is a free trial license that comes with sort of certain restrictions, one of which is basically that if you are using it, you are not allowed to make or state sort of any claims on the performance that you measure if you are measuring performance with that executable, which puts us in somewhat of a precarious position if we are talking about performance, in that I think maybe we'll probably have like a part 2 and part 3 going forward on this kind of topic. So in the future, if either sort of via the KX company or First Derivatives, or sort of, if Steven is able to say certain things when he's on in the future, we might be able to talk about it then. But I think for the purposes of today's episode, we're probably going to focus more on APL, J, and BQN, because we can say whatever we want about those languages without worrying about, I don't even know what would happen. Legal, would Arraycast get sued? I don't know. Would we get taken off the air?
They would start with a cease and desist. I don't know where it goes after that, if they decide we're worth their time.
Yeah, if you're wondering where Steven is, he's had prior plans today, and also we're probably not going to mention a bunch about Q. Feel free to write your local KX representative if you'd if you'd like a change in that policy. But with that out of the way,
well, actually, I was talking about policy. I think in some ways that policy is reasonable, and we'll probably get into it during this episode. But if you allow people to publish that kind of information, they can control the situation that they're running it under, and they might have come up with results that are entirely valid for what they're doing, but not fully report how they're getting those results. So I can understand why a company might do that, because they want to control that what they present and hopefully is valid. It closes the door in being able to be open about it, but it opens the door in terms of what they present should be valid for what they're testing.
But it is worth noting that neither KX nor Shakti, as far as I can tell, present any benchmarks of their programming languages as array languages. So they don't test against APL or J, from what I've seen. They publish benchmarks about its use as a time series database, and that's all.
And that's their language is tuned to the database.
Yeah.
Like, does the language really exist aside from the database? I don't know. It's a language, but you need the database to really run it, don't you?
No, you can just like run code in Q.
Yeah, I don't think of all the Q code, which admittedly probably is less than like 1,000 lines of code, which still is substantial considering you can do quite a bit with Q.
Considering it's Q, yeah.
I don't think I've maybe written like 2 or 3 KDB plus like queries where you're using like the where keyword and stuff like that. Like most of the stuff that I do is leaning on the reduction and scan primitives and stuff like that. So it's very possible to use Q as sort of more of like an APL or J or BQN like language versus a database querying application.
And I guess I'm thinking with Shakti, Arthur's providing the databases that he's running it against, whether it's the taxi database for New York or those kind of things. Those are available.
Yeah, Shakti's shown some benchmarks on open databases. It's not, they haven't shown source code or anything of like what they're running, but I think if you were a client, you would be able to reproduce what they do, but the rest of us just have to kind of take their word for.
Yeah, I was gonna say that like on one hand I agree, Bob, but like I really don't. In that, like from a programming language enthusiast point of view, like it's kind of the equivalent of like a language like Rust or Zig coming out, and they're trying to compete with low level, performance, heavy hitting languages like C++ and C, and then saying that they want to protect the reputation of the language because people are going to go and run sort of faulty benchmarks, which like admittedly there's tons of people out there that are how specific are they, setting, and there's even a bunch of talks. There's one by Emery Berger who talks about how when you're profiling stuff on a computer, like so much stuff impacts. Like one of the points in his talk is he's working with a student and can't figure out why something is running so much slower on his computer versus Emery Berger, the professor's. And they realize that it's because of the length of his username, which is in like the present working directory. Like, so it makes the length of like, PWD that much longer. And somehow that leads to like a 10x.
Well, it changes the alignment of the interpreter, or the whatever they're running, the binary, where its addresses are located in the memory space. And I still don't understand why this is, but with the way CPUs are designed, they'll run your code at different speeds if like the loops are aligned at different positions.
So it's the location of the program on the disk itself?
Yeah, so the alignment of the addresses, like if it's an address that's a exact multiple of 16 or something versus one offer, that changes performance. I don't really understand why. I mean, like if you're running a loop like that, all the code should be in the micro-op cache. I don't get why that happens, but I've also seen, up to like close to 2 times factor, like for a small hot loop, just based on, like you'll change some code that's some other place in the interpreter, and you'll run the exact same code. It's the exact same machine code. You can look at it and check, and it'll be at different speed based on how it's aligned. So yeah, that's very annoying as an implementer.
Yeah. So the talk that Emery Berger gave, who's a prof at, I want to say UMass, but I could have that wrong. He basically shows all these like foot guns and things you totally wouldn't expect that are like affecting perf and profiling, and then introduces some framework called Mesh that its goal is to like basically randomize like a ton of system environment variables and all these different things that you wouldn't expect. And so you're kind of doing this like random sampling of stuff that supposedly is supposed to make, the profiling more accurate. Anyways, this is all to say that I agree profiling is a tricky thing. That being said, especially when you're sort of releasing a language, it is, I would prefer to be able to, compare it versus other things, right? Like if Rust came out and said, sorry, no, you cannot, we will come after you if you try and compare us against C++, like that would kind of be like a non-starter.
And by the way, here are benchmarks against C++. You don't have that. So you don't have that check where, and this is, to be clear, KDB has not done this against APL, but they've done this against other time series databases. You don't have that check where the other database vendor is able to say, well, you did this wrong and that wrong by reproducing the benchmarks and going through. So, if a K person was to run a benchmark and they saw, oh, K's out, way ahead, they probably wouldn't question it and would say, all right, well, this is a good benchmark, let's go. Whereas then when the other database maker is seeing this, they'll say, well, that's wrong. My code shouldn't be that slow. It should be able to do this thing fast and be able to check that.
Yeah. And a great example of this is when I was doing some benchmarking stuff, I had sent it sort of internally, and then Marshall pointed out that, BQN I was basically profiling the 3 consecutive odds problem if you've listened to my other ADSP podcast. And it basically involves a sort, adjacent comparison, which you can spell different ways in each of the languages, and then a reduction at the end of the day. And obviously, anything involving a sort is going to, obscure stuff. But Marshall pointed out that the way I spelled it in APL using sort of a point-free fork was not optimized at all. And he said, you should switch that to a defun. This is the actual sort idiom that is like performance optimized. I had no idea. Sure enough, I went and ran it, and then it was like sped up way faster. And that's the kind of stuff that Marshall's talking about. Like I can go and mess up as someone who's trying to profile stuff and then put it out on the internet, and then people will be like, oh, actually, this thing is optimized. If you go and do this, you'll actually get what is possible with APL. And there's no way to do that kind of stuff if you've got some restrictive, clause in your license that says...
Yeah. I mean, but that's a big problem with APL too, isn't it? That the obvious thing is not the fast thing.
No, you'd like it to be, wouldn't you? Yeah. I think that's true.
Yeah, and so I mean, there's a question of what is your benchmark measure? Do you want to measure what the best performance you can get is, or do you want to measure what a typical programmer would see, or do you want to measure what a new programmer would see? Or I mean,
if I had to pick, typical sounds reasonable, doesn't it? But
all right, yeah. So just find some typical programmers and have them all write code. And
well, I think
make sure they're all exactly as typical as each other.
So I'm not really like a hardcore low-level programmer or a performance buff particularly, but I did one video some time ago about reasoning about computational complexity in array languages, and that's one thing that you do have, which is the ability through the way the primitives are constructed and put together to actually think about how these short expressions should perform in I guess the worst cases, if you're talking about computational complexity. But then in real applications, what happens is you find, this thing that lots of people are doing, the way they write it in APL the way you have to write it, or it's nice to write it in an array language, and then executing each of the primitives one by one isn't quite as fast as if we did the same, thing overall. But we know of some clever algorithms that we can code in the interpreter. So that's kind of part of what you're talking about with these hidden tricks that you might not know about. That also makes it makes it difficult to know what's the best thing to do. But on the other hand, you have this simple set of rules for most of the language for the typical cases, which I think is really beneficial.
I think a part of it is also like PGO, like profile guided optimization. And as you start to learn a language more and more, like at first it may not be the typical thing to do, but as you become an expert in that language, the things like Marshall pointed out. And like one of the other things I quickly discovered is that there's no equivalent of like an n-wise reduction in BQN. And up until doing this profiling, I had always done the moral equivalent or spiritual equivalent, at least of what I thought, which is like, I believe it's called Windows, which is the dyadic form of range, which is the equivalent of iota in APL. So you turn a rank 1 array into a matrix and specify how many elements do you want on each row. And once you have that matrix, you can then perform a rank 1 operation on each row and get the equivalent of a sort of sliding reduction or an n-wise reduction. But in profiling that, I realized, holy smokes, the creation of that matrix is brutal. And really what you want to do is like a drop 1 and a drop -1, and then you've got like 2 different arrays that you can just do a binary operation on. And that is the performance equivalent of doing the n-wise reductions. But like that's the kind of stuff is that like now I know I'm probably still in YouTube videos going to do the Windows reduction because it's easier to spell and I think closer to what you can do in other languages like J and APL. But knowing that if I actually want like the performance equivalent of what I'm doing, I need to spell it this way. Like that's the kind of stuff that you start to learn. Like, would it be ideal if BQN had some version of that, n-wise reduction so I could save myself 3 characters or 4 characters and still get the same performance? Absolutely. But like that's, I think learning any language, you just need to start to pick up those things over time to know like, is performance important here? If so, use this method. If not, like the exact same thing happened in the video I made yesterday. I did to sort a list of numbers in reverse in Python. I did sorted, paren, the list of numbers, and then bracket, colon, -1, end bracket, which is like a shorthand shortcut for reversing any list of numbers. And I got like 4 different comments on YouTube and 1 on Twitter that was like, there's a parameter to the sorted function that is just reverse equals true, which is much more idiomatic and much more performant. But I even said in the video, like, this is probably not the best way to do this, but it's it's the tersest and what I want for the purposes of this video. And anyway, so it exists in every language, including the most popular ones in the world, like Python. Ramble over.
Yeah, I mean, so there's a big question of like not only what's the fastest the language can achieve, but does the language guide you to better performance, which you're not going to see on a benchmark because the benchmark usually tries to show, how fast does the good way to do this perform, not, how many tempting bad ways to do this are there. And Windows and BQN is definitely a problem like that. There are designs for Windows that would perform quickly, but what I was thinking when I designed Windows was trying to make something, that's more approachable for someone coming to BQN. And I decided what I wanted to do was to have, the rows be windows. So you can easily see your left argument says the length of the window. So if I do 5 windows, I get all the slices of length 5. So at least if you have a short window, the more CPU friendly way to do this would be not actually to arrange it like that, but instead have a list of 2 lists, where the first list is all the first elements of every slice and the second list is all the second elements of every slice. And so that way, if you do a subtract reduce on that, then you can subtract those 2 lists and it'll work out quickly.
And from a compiler point of view too, or I guess it's interpreted, but like you could.
No, it is. Well, it's compiled some and then interpreted some, like pretty much every language.
So I hypothetically though, like you could put in some kind of optimization where you recognized a sequence of primitives that is windowed followed by a rank 1 reduction on rows, and encode that so that you don't have to materialize that rank 2 matrix. Like,
yeah, and we've already made some improvements to windows that were based on what you were measuring. I've noticed another benchmark with Windows too. I didn't really think people would be benchmarking with it so much, but apparently people really want to do like NY sums and stuff when they're benchmarking.
I mean, I have like in my top 10 GitHub repo where I compare different problems. The only one where APL is the winner, I think so of the 8 problems, I think BQN probably wins 5 times, Haskell wins twice, and APL wins once. And the only one where APL wins.
And this is in terms of how nice the code is, you're saying?
This is completely subjective. It has nothing to do with performance. It's like how much I like the spelling of the solution. That's it. Like perf doesn't matter. It's elegance and, beauty is in the eye of the beholder. And the only one that APL wins in is the 3 consecutive odds, because specifically it has an n-wise reduction where you just are passing this binary operation to a higher order function, essentially, whereas in every other language, you have to do something a little bit more verbose, or it's something not as elegant. So like in general, I think BQN has a lot more things like under and inverse and more combinators and the sort primitives, and I could go on and on. But there are like, at some point I'll make a talk of like a Venn diagram of the features that like all array languages have, and then like what BQN has that the others don't, what APL has that the others don't, and what J has that the others don't. And I think like that, I mean, I actually don't want to make that video. I want someone else to make it, but no one else is going to make that video. So.
Yeah, and as you say, it's subjective, and I guess we'll never know for J because our digraphs are just inherently ugly to you, aren't they?
It's every once in a while I do solve a problem in J, and then I'm like, this is close, but it's just always there's like 1 or 2 or 3 extra characters. I think the closest J might win if there was something involving primes, because you do, or like you get to the more esoteric that like is specifically built on some math function, and then I discover, oh, J actually has that math function. But yeah, there's hope for J. I still
I don't, as long as the big issue is whether we have dots or colons following our primitives, I don't think there is hope for J. But that's okay. We don't mind.
No. But we haven't talked to Henry yet too. Is we got the upcoming fold episode, and from my understanding of folds.
But those have dots and colons.
But if you can spell like the double fold pattern that I'm trying to think of, which is actually, it's poorly named because there's a single fold. It's a 1-pass thing. What should we call it? Because originally I was calling it a 2-operation fold, a 2-op fold.
Do you mean like a fold over 2 arrays together?
No, it's like it's a scan followed by a reduction. On my other podcast, our guest Zach called it a scanduction, but it's the idea that like you don't really need to do a scan followed by a reduction. In a sophisticated enough compiler or interpreter, it would see the juxtaposition of those 2 things and go, really, we just need a single reduction that's carrying 2 pieces of state and throwing 1 away at the end of the day and just returning 1.
Oh, yeah.
I'm not sure if JFold can do that. I know it can do things like that. But anyways, other episode, we're talking about performance right now. There's hope for J.
But now is the time to say that performance really doesn't matter.
All right. Go ahead, Marshall. Tell us how you feel.
I feel like performance is something that is that's very prominent, that people use to that they do use to investigate which language they would like to learn, that they use to justify their choices of language. But really, performance is not that much of a concern in whether a programming language works for something. And so you see, in terms of practical use cases, like APL has a few efforts that are solely aiming for performance, like the Apex parallel compiler is an early one, and codefins is one now. And what you see is people don't use these because they have less features. So
they don't use them, or they only use them?
They don't. I mean,
no, yeah,
like,
they don't use them.
I have no evidence that and Dialog APL is used by all sorts of companies and stuff. As far as I can tell, Apex and codefins have never been used for a major project. And
you're saying this is because it has a subset of the full functionality provided by Dialog APL, which is where most APL people are coming from.
I mean, so that clearly establishes that, the number one thing is to have a comfortable programming environment. And I mean, this is in the domain where APL is dominant. I mean, there are other domains. So, but in these, I mean, people are typically writing, the direct low-level code. They're, writing GPU shaders and stuff like that to really get full performance out of whatever hardware they have available. But in the domain where APL is, which is I have a problem and I want to solve it, generally the CPU can solve your problem in a very short amount of time. And so, I mean, yeah, if APL was a million times slower, that would be a problem. But, getting another factor of 10 out of APL is not actually that much of a benefit for what the users see.
Right, I guess a lot of the optimizations of the array primitives, like where it matters doing, SIMD style processing.
Yeah.
That stuff kind of already existed anyway. So those types of performance optimizations happened in bits and pieces over time in the cases where people might have relied on that. Now having the environment is far more important than we say 10%. I don't know what we need more Codefense benchmarks.
Yeah, well, it's not a matter of like, oh, if you just had enough of a performance increase, it would matter. It's I mean, for every task you do, well, for most tasks, I mean, there are some things that you can just pour more and more processing power into. Finance is a good example of this, because ideally you would have enough computing power to figure out exactly what everyone else is going to do. So you need more computing power than the rest of the entire market. But most things, you have a task to do. You want to process some image, apply some operations to it, and once you finish it, it's done. And so then the speed, as the speed increases, you go from this is just impossible, no one would ever wait for this, to you need huge amounts of processing power, to, well, you can finish this on your computer, but on your laptop or whatever, but it's inconvenient, to this finishes as fast as you can even ask for it. And at that point, no amount of performance increase is going to do anything for you for this particular task. Now, people do a lot of things, and some people, I mean, most people have something that they need to do that needs to be really fast. And I mean, for those, there are lots of tools and tricks that you can reach for. But for other things, it's like, why are you chasing the fastest programming language when there are tons of programming languages that are fast enough?
Bob, you were going to say something?
Is it like to take it back a step, I guess, in terms of performance, is it possible to evaluate languages based on how they can improve their performance? In other words, there are some languages that typically, because they focus so strongly on performance, and I do think K is probably, or Shakti is one of those, that Arthur is so tied into performance that he's just going after that fast. Mm-hmm. And so it's a language that is going to be at least focused on performance. There's a lot of other things about it, but one thing is he will be making it as fast as it can. Other languages aren't like that. Is that a valid way to evaluate a language, to whether one of its focuses is to be performant or not?
If you're doing stuff in the domain where it claims to be performant, I guess.
If you are in that rare case where you need the top performance, then you don't want to pick something where there's no performance concern at all. Although really there are not that many mainstream languages that aren't optimized in some way. It's just a matter of what things are good for. I mean, some language designs are inherently, held back by various concerns about, like, having features be possible for the programmer.
I guess I'm sort of dancing around the topic, though. Taking it out of the array languages, for something like Python, I don't think very many people claim Python is inherently performant. It's not really fast.
No.
What it is good at is providing lots of glue.
Although it is, over the past just few years, it is getting a lot faster. So it's becoming a worse and worse example.
Okay, but fair enough. But the thing is, if say 10 years ago you started with Python, you weren't choosing it.
Hopefully not.
Oh, well, I guess that's the question. Can you evaluate a language based on its potential to improve?
Right, you weren't using it 10 years ago because you were hoping in 10 years it's going to be a bit faster either. You're using it because you can just look up some docs for a package with an API and plug your data in and get the answer in like half an hour.
And that's your performance, right? It's not the speed on the machine; it's the speed.
Right. Programmers are expensive, yes. Yeah, computers are relatively cheap.
I guess my question is, and maybe you can qualify your statement, Marshall, if I'm understanding what you're saying. Is you're saying, for at least what I heard, was that in the domain in which APL and array languages operate, for most cases, performance isn't really the key thing people are reaching or using those languages for. And my question is like...
Yeah, it may be the thing they're asking for, but in that case, they're often misinformed about what they really need.
Yeah. So I guess my follow-up question to that is that just a function of what APL and the array languages evolved to be? Because one of my evolving theories is that, from what I can tell, reading Iverson's papers and his work, he did not care about performance or like the implementation.
And I'd agree with that.
He cared about notation as a tool for thought and the functionality of what you could do with the primitives and the choice of primitives. And I think because of that, my kind of theory is that these languages evolved to, in a way such that that's not what the programming language implementers were concerned. It wasn't their primary concern. Therefore, you end up with languages that aren't extremely performant. And then when something like machine learning comes along, which is just a bunch of matrix multiplication, the language that is chosen for that is not these array languages like APLJ, which to me seems like the missed opportunity of like a century, that we had these languages where the primitives were arbitrarily ranked arrays, but they weren't chosen because they didn't have performance as like one of their top three things. Therefore, they weren't a good fit, because when you're doing choose your AI application, self-driving cars or, optical character recognition, there's a bajillion of them. You're not reaching for APL. And there's been papers. I know there's one by Bob Bernecki and friends on like convolutional neural networks and APL. But the hard truth is that like these languages are not used for these performance critical applications that involve sort of neural nets and AI, different techniques. And I think that like if history had evolved differently so that there was a language, an array language, maybe not APL or J, but one that was, and that's the thing, is technically, we're not talking about Q, but like you could argue that, K and Q were the performance sensitive ones. But as we mentioned, they were focusing on Wall Street and time series databases stuff, not on the, matrix multiplication and the stuff that's necessary. Anyways, I'll stop talking. Like, I'm interested to get your thoughts on like that sort of angle. Is it a self-fulfilling prophecy or is it something different?
Yeah, well, I have a few things to say about that. The first is that early APL implementers were definitely concerned about performance. APL was pretty competitive, definitely with other interpreted languages in the early days. And even APL 360 had packed bit booleans, which is a pretty fancy optimization. And APL is also the APL, implementers did one of the first just-in-time compilers, which is APL 3000. So there was a whole lot of work on performance in APL in the early days. The other thing to note is that although Iverson did not care about performance, he appears to have been very lucky in stumbling on this paradigm that is inherently high performance. So much so that some of the vector instructions in CPUs now in AVX 512, to compress and expand instructions, are just lifted directly from APL. Like,
wow,
they took APL functions and decided this was the best way to make CPUs faster. So I don't think the problem in APL getting picked up was anything to do with performance, because it definitely had those capabilities. And sure, there was no APL that was, that did general APL stuff and was running on the GPU at the time that people were picking up machine learning stuff. But what won against APL, it was custom frameworks that were, all this TensorFlow. I think it was really TensorFlow in the early days and
then PyTorch later on
was the one. And then later stuff like PyTorch, but stuff that was purpose designed for machine learning. So they said, all right, we have these machine learning problems. Deep learning is getting a big field. we will design these frameworks especially to work with this and to run quickly on GPUs because this is our requirement. I don't think there really would have been any problem doing this with something APL-like. What I've seen, and I don't know a ton about machine learning, but what I've seen from like machine learning and APL papers is that the solutions they have spend quite a lot of time doing like writing manually out like what you do for backprop and stuff like that. And that's TensorFlow's big advantage is doing that for you automatically. So I would really say the thing that made TensorFlow, that put TensorFlow ahead, was actually having a better feature set for machine learning. And secondarily, the performance, because I mean, you do need to run on GPUs if you're going to learn anything fast.
Yeah, I mean, most of PyTorch and TensorFlow and all these frameworks are tied in. Like they have multiple backends, but like I know specifically PyTorch, one of the backends is like cuDNN, which is a library that NVIDIA makes. So like there's a high level part and then the backend part, and the backend part typically is not, it's written by, I mean, maybe some of the backends are written by folks at Facebook or wherever the most. I know it was a Facebook project at one point. But it's also hooking into, tuned GPU code that was written by GPU experts at NVIDIA, right?
And I mean, it's also worth saying that what these frameworks are actually running now is low-level intermediate representations that are designed specifically for machine learning. So if you want to build any language you want to on top of those representations, you can do it and compile down to MLIR's one, and then get good machine learning performance. So, I mean, yeah, the performance of the language is not actually a challenge here. It's getting a language that people want to use for their machine learning.
And that might be purely familiarity.
Oh, yeah, definitely. I mean, I'm not saying that PyTorch is, inherently the fundamental best way to represent these machine learning operations. I mean, it's definitely got some stuff that's chosen to work with machine learning that's pretty nice, but I mean, a lot of it is just what looks like the sorts of mathematics that people are familiar with, or what looks like, what's easiest to explain based on people's past experience and that sort of stuff. But yeah, I think it is primarily a usability problem that these new machine learning frameworks solve instead of, it's a problem of having the usability in a way that the CPU can optimize at all. So, I mean, if you write nested loops in C, you could probably write machine learning that way. I mean, I also don't think that would be as ergonomic, but also it's pretty tough to get that to run on the GPU, right?
I guess, for Jay, we're waiting for number theory to take off because,
yeah,
we're gold then.
Well, quantum computing's got some number theory going around there.
Yeah, I mean,
a little bit.
The question is, as you say, is if say you took something really wild like quantum computing, wherever that goes. I mean, it's the cold fusion kind of our age right now. But if you had libraries that made that easier, your language would probably take off if that became more popular and became something that could be done.
Yeah, but in this specialized domain. So I actually do think it's really great that, APL has remained a general purpose programming language, because now anybody who wants to learn APL or one of the languages in that family can then be able to apply it to problems they're familiar with. Although, I mean, some areas are easier than others. All the web stuff is pretty tough, because then what you want is a bunch of interfaces, to connect existing, connect whatever the server gives you to your piece of code or something like that.
It seems to me some of the challenges, the critical mass of the number of people actually who know the languages and then would produce libraries and would be interested in those developing areas, and whether they can compete against a much larger group of people who are working on bigger projects and have funding and a number of other things behind them to swoop in. I'm trying to think of the Y Combinator, Paul Graham, talking about his magic, wand was Lisp, that he could program things in Lisp, and that gave him an advantage over other people.
Yeah.
I don't know whether, if you don't have a critical mass, whether that's true of the array languages anymore. I think some of these other languages have got so big with their libraries you might stumble on it. I mean, there's always theory, and there's always things like number theory where if you get the right person thinking about a problem, you can solve a problem very quickly. I think Bob Brudzewsky had a paper about big tin versus algorithms, which is really good. Because if you get the right algorithm, you get the right thinking process about it. I guess that comes back to what I think are the gold about these languages is I think they help you think about problems. And I think that's their magic.
But it's no substitute for having somebody else think about the problems for you. So
that's true.
Yeah.
Or have a whole group of people think about the problem.
So, I mean, APL is a great paradigm and it scales well. But what also scales well is just having one person solve the problem and then everybody else use their solution. And then the programming language doesn't matter so much. So,
well, I've been what's the word, mulling over what you said. Because I work at NVIDIA, so I know that there are a certain category of companies and individuals where performance is, they're running, the scale of what they're running it's immense, and perf is it's non-negotiable. And those are the kinds of people that even if they have to go and program in a less ergonomic language than Python, such as CUDA C++, they will go and suffer through. I won't say suffer, but it's definitely not Python, and it requires a higher level of expertise. But they're willing to do that to get maximal perf, even if it's less ergonomic. And a part of my job at NVIDIA is trying to create a better story for that. Ideally we could have a more ergonomic language and make it easier for individuals and companies to conveniently and expressively solve their problems and get maximum perf at the same time. So that category of person exists, but when you sort of mentioned that, I don't think it's really perf that drives that. There's no reason that APL or J or some array language couldn't have been the lingua franca for machine learning and deep learning. It was more that the ecosystem didn't exist and the popularity might not have existed. So the lingua franca ended up being Python, which was better suited for, or not even better suited. It was just a more popular language at the time, and certain people started creating libraries, and then people started speeding up the backends to.
Well, and you can't say in any sense that the high performance code is written in Python. It's written in a Python library.
I'll find a meme that is a Corvette. It shows a Corvette and then it says Python on top of it. And then the next photo below it is the Corvette on top of a truck that is carrying a bunch of cars. And that truck is C++. And that's the joke, is that any performant library is really actually on the back end written in C or C++. And if it's actually performant, it'll be a multi-threaded or GPU accelerated thing. But I guess your sort of argument is that you need to put your language in a place where it has got enough of a following and enough of an ecosystem so that if it comes to a point where performance is actually something that you need for your application, you now have that ecosystem that says, hey, we have this library, let's go create a new backend and bindings, and we can go write the backend in whatever performant language you need and accelerate that, which then kind of makes me think.
But you've added, you've just added the big caveat of backend and, a pluggable API, this type of abstraction that actually the array languages are kind of antithesis to in some ways, right? In theory, you should have we've got a primitive called reverse, and for whatever data you've got, this is going to be the fastest reverse that you can, fastest way of turning the array, the elements in the array the other way around. And it's only when you get to this whole string of things where, you've written it in that way because it's a really nice way to express it with these primitives with the syntax. But actually, the thing you're trying to do, there's this other way to do it that's way more faster. Whereas in Python, you don't care because you've got this name over it that's abstracting away the details of how you're actually doing it. But that also means that you can just go ahead and swap out the back end with, this thing written in Rust or whatever.
The follow-up to my sort of ramble is that there are languages, funding. When we had Trolls on, we got the whole story of how funding was and grants were given to the University of Copenhagen, which led to a couple different projects, but the one that sort of still exists today is Futhark. And on top of that, I believe his name was Bodo Scholz, has the single assignment C language, which actually is similar, closer to Python, as you just mentioned, and it actually does have multiple backends. I think it has a CUDA backend, and it has a couple different accelerated backends. But like, I don't think anyone would disagree with the statement that like those languages have not succeeded at like a sort of large scale. And so when you say, Marshall, that there's no reason that, that language kind of couldn't exist and couldn't be successful, my mind goes to like Futhark and single assignment C, which haven't really been successful. And my question is then like, was it just the ecosystem and popularity of Python? And it was like history would have had to evolve differently in order for a language like SAC or Futhark to be the go-to? Or, why is it that people are coding in Python and not in some accelerated array language is, I guess, my thought.
Well, I mean, there's different things. And I think, for Python, the answer is pretty easy. I mean, people like programming in Python, and that's all there is to it, because performance is not a consideration there.
I love programming in BQN. I just made a video about it on Monday.
But I mean, there is this other segment that's the people that want the most performance possible. And I think Futhark fits pretty well in that segment. And it might see some uptake. Dex is another one that's produced by Google. And I think that may be seeing some use.
We should have someone from Dex on.
I mean, these have fundamentally different goals than APL does. They start with saying you need to get the full performance out of your GPU and, be able to use all the capabilities that it has. And then they build a language around that. And that involves being able to do some stuff that, it's kind of a completely different execution model from APL. And it involves, cutting you off from using like first class functions in certain places when their particular methods for taking things to the GPU don't support what you're doing. Where APL is designed, the completely other direction. What's a good language for working with these arrays and stuff? And what's amazing is that gets you, very good performance by interpreted language standards and even pretty good by compiled language standards. But it does not get you good performance by these restricted compiled language standards where you're giving up some programming capabilities in exchange for performance capabilities. So, I mean, that part of the market, you would have to do something to APL. And I mean, that's kind of what Apex was trying to do. Maybe you can argue that Apex was too early for it.
But it's also, you said about like people don't use code defense, and that is true. But what I think the usage model, I think for some people is supposed to be a bit like this, where you've got some part, your application you're writing in the language where you appreciate all the features of being able to do whatever you want, in the way that but then you might have some part of it that is performance critical, and then you can just like encapsulate that in a namespace, send that to codefens, it turns that into compiled code, which gives you that same API that you wrote as a function back, and you just send your data to it that way. You just have to like have a part of your code where that matters.
Yeah, well, and I think codefens also has the problem that, I mean, for the segment that Connor's talking about, I mean, for the people who are currently using APL, it's pretty good because if you can write in this subset of APL that's supported, which is a reasonably large subset, then you're good and you can speed stuff up. But it is not as fast as something like Futhark, where you can specify the types of everything and have a closer correspondence with what the GPU is going to do. So
and at a certain point, you're then reaching to a library written in Futhark, compiled to a binary, and then just hooking into that with whatever foreign function interface you've got, which are back to the black box of the different backend solution.
The reason for this is that codefens is is still trying to support, the normal APL. It's not. Apex did some stuff. I don't know if it was enough. I mean, I haven't used Apex. I've only, tested out codefens once or twice. But from what I understand, I mean, to get things to run on the GPU, you have to know exactly what types are. You have to know how they're laid out, and some things that are like, you can get a compiler to do it from APL code, but it's not going to do it very well. And so you're going to get performance that's still a long way off from, actually definitely from somebody who's writing, the C++ shader type code for a GPU. And I think also from something that's written in Futhark, where it's the language that's designed around being used on the GPU. So, I mean, I think the stuff that's designed for GPUs can still pick up a lot of useful things from APL, but I don't know if necessarily the way to go is taking APL and trying to run it on the GPU, because then you have a lot of difficulties in having the programmer supply enough information to tell you how it's supposed to be compiled for the GPU.
That's a big problem coming from a dynamically typed. Like that's for anyone that's programmed in Futhark, very quickly something you'll come across is that you have to type, if you want to do a maximum reduction on a list of things, you're going to have to, not for all the primitives or functions that are in the prelude, but you'll have to call i32.maximum. So you have to specify, the type of the reduction that you're doing, which is clearly anathema to any of the Iversonian languages where that stuff is implicit. Which it's not, doesn't completely.
Well, I mean, but I can jerk us around a little. We've been talking about the GPU, and I don't think APL is that strong on the GPU, as I've said, but it's really great on the CPU. And actually, I think that not having these types specified is a huge strength on the GPU.
CPU.
On the CPU.
I was like, what? You don't think it's a good fit, but it's a huge strength? I was like, Marshall, choose a lane.
Right. Unspecified types, good for CPU. Go.
Yeah. So I mentioned even back in APL 360, they were doing packed bit booleans, where your array is, if your array consists of zeros and ones, and the language figures this out, I mean, say it's the result of a comparison, then it's always going to be zeros and ones. Then it stores it packed. So each byte stores 8 zeros and ones. And this is, 8 times more compressed than even storing 1 bit in a byte, which is actually typically what a C programmer would do. So you get this enormous advantage of having the data smaller. And this also means that faster algorithms can be used for that. So for example, if you're summing an array of bits, there are actually too many methods to even go over, but there are a whole bunch of ways to sum a bit array that are faster than expanding to bytes and summing those or something like that. There are all sorts of other, and like if you want to sort an array of bits, that's not terribly common, but there are other related things. If you want to sort an array of bits, you just count the number of ones in it. And then, from subtracting the number of zeros, and then you write out that many zeros in order and that many ones. And so that's much faster than it would be sorting with a comparison function or something like that. So being able to compress these types, even when the user doesn't ask for them, gives you a pretty big performance boost. And what that means also is that in cases where the user wants the safety of a large type, so I mean, say you're doing some sort of financial software, like a financial database, and I mean, you don't expect any of the users to have over $1 billion, but maybe someday it'll happen. What you do, I mean, you don't have to specify a type. You just say, well, each user's amount of money is a number. And then I mean, this is not actually good with finance because you're supposed to use decimal floats, but you can do that in dialogue. But you just know that the amount of money is a number. For most things, a double precision float is good. Finance is like the one thing where it's not. So I messed up on the example. But you just say it's a number. And then, if everybody doesn't have $1 billion, then it, and they have an even number of dollars. So I need a different example. But if like the number of cats they own, I mean, that's never going to be higher than 128. And it's always a whole number. So that's good. Then your database can optimize that and say, well, I'm going to store that in a 1 byte integer and do all sorts of fast stuff with it. But you have the safety. If anybody ever does acquire 128 cats, you're still going to get the right answer, just a little slower. So, I mean, that in stuff like text processing, where all your indices are typically less than like a 2 byte integer, because, the text file that you're processing is probably just not that big. That's a big speed advantage. And you get that with the full safety of having a large numeric type backing you up.
Aside from counting cats and high finance, I'm going to toss out an analogy that's been going through my head right now. That's kind of builds on what Marshall had said earlier, that performance maybe isn't the most important thing in some of these languages, or maybe any of the languages. And that is, if you use the analogy to music, I don't think there's anybody who would dispute that Eddie Van Halen, say, for instance, in a rock band, Van Halen, was a virtuoso guitarist. Many people have said, somebody like Prince, another, incredible guitarist. But you wouldn't say that they're necessarily a better musician than, say, Yo-Yo Ma, who, might be part of a string quartet or plays the cello. But they're two very different things. And so, in essence, I guess what I'm saying, in some ways, rock bands are kind of like the Python. They've got a big audience. You're unlikely to have a huge audience watch a string quartet. Even if you could in a huge, arena, you're probably unlikely to want to watch that sort of thing that way. So you're kind of choosing what you want to watch. The type of music dictates the size of the audience to some extent. And I think some of the array languages, if they were to make that crossover, they have to make the case that, like a crossover between genres of music, you have to be so popular that they'll bring you across to be in a different genre because you're that good in that which you do. But if you don't make that jump, you'll be known in another area, and it may never, ever get that big. I don't know. Does that analogy make any sense at all?
At the end sounded a bit like regular expressions, but...
So the idea is like, how you could bring APL to a bigger audience?
Well, the idea is that if APL is to reach, like what we talking about with some of the other languages that have taken off with machine learning.
So like Van Halen is the Python or whatever, right?
I mean, Yo-Yo Ma is pretty popular, so I don't know.
Yeah, no, that's a case where...
Yeah, you need a worse cellist.
Who's a more obscure cellist, yeah.
Yeah, but he's one that's made that crossover. So he has been so good and so popular. But I don't think Yo-Yo Ma plays arenas. I know he plays big concert halls, but I don't think he plays arenas.
Yeah, which are really not even the same order of magnitude, are they?
It's true that some people hear about, APL, languages where the basic data type is arrays and certain things are optimized for arrays. And then I guess like Conor was expressing earlier, you get this impression that, well, okay, these types of problems, they should be like rocketing through with performance. They should be the best thing. And there's quite a steep learning curve as well, right? So there's a fairly significant amount of effort you have to put in to gain proficiency in these versus certain other more arguably accessible things. And maybe there's that feeling that like, well, okay, but if I knew that after all that effort, I would get like the most performant language, then I'd be willing to put in that effort. And we're kind of saying here that maybe that's just not really the case.
But I mean, then there's that most. I mean, I can with BQN today run, 100 times faster than anybody 20 years ago could accomplish with like, well, I mean, maybe on a supercomputer, but and then go back 30 years or 40, and even the supercomputers aren't going to do it.
Yep.
So why are you saying that my goal is to get the most performant language instead of just outstanding performance? I don't want to say best, but I mean there are some things in terms of expressivity that APL can do that the APL family can do that you just don't see outside of there. So
I mean that's a much harder headline sell than fastest fastest column stored database time series.
And in some areas like financial, the sell isn't to a CEO that you can program this computer to be the fastest thing ever. It's that we can put people in your company who can do that for you. Nobody's expecting the people who are making decisions to be able to do that, but they're saying this is a tool that you have people that could use that would make you that much more powerful. And so I think the part of the learning curve, I think, is an important part of it. And it's similar, to go back to my music analogy, I think there's a little bit more to music appreciation for the general public if you were into classical music than there might be for rock and roll. I'm not saying there's not a huge level of appreciation within rock and roll. I'm saying if you take the typical, again, normalizing things, take the typical classical music person, they're probably going to be aware of more things about the music than a person who wants to watch a rock band is. Just because of the immense power that's coming off the rock band, that's the visceral thing that person will pick up first. After that, they might get into musicianship. I think classical music, people are going to appreciate musicianship first. And so that's the learning curve to get into classical music. And maybe opera is a crossover of that because it has a visceral push, and more people are becoming interested in opera or music theater because it has that push of emotion.
I think the one of the really big strengths of APL actually is that you don't have to learn a lot of specifics in order to get good performance. So you need to be able to solve your program with APL, which is a big learning, or with array programming, not just, you can't write APL like Python and get good performance. But what APL does for you actually is by using pretty normal strategies of just writing things with arrays and doing things that actually, also at the same time improve your ability to solve problems quickly and write, less buggy code and things like that. You can get good performance without knowing a lot about the machine. Like the array, the language implementers are the ones who have to learn all this fancy stuff about branchless programming and SIMD and caches and all that stuff. And then if they've done a good job of that, you as the array programmer can get, world-class performance. And actually faster than C at times on the CPU. I've mentioned this on the podcast. We did our bootstrapping compiler with BQN. And we wrote the C program in the way you would write a fast C program. I don't know how to speed it up. And it's slower than the BQN program. So not on the GPU, but on the CPU, where you're running completely general code, you can actually get, even faster than compiled languages with BQN in this case. But all you have to know is what operations are going to be good. So things like plus scans are good, reductions are good, and the basic primitives working on lists. And you need to know how to break your problem down in terms of those. But if you can get those down, you can write all sorts of text processing tasks and have, really high performance without knowing much about the machine or, really anything.
And essentially, I think that's what Arthur has done with Shakti and the different versions of K is he's tuned the machines to do a specific task very, very quickly.
Yeah.
And it's a task that people require to be done. And they don't need to know. They are standing on his shoulders to be able to do what he can do at the lower level.
Well, and if times change and, different factors in the machine become important, and I guess we'll start to see, some GPU integration in array languages as implementers start to get a handle on how to use GPUs. As times change, you write the same array code, and it is updated with the hardware so that that same code runs faster.
And that's where the advantage of being able to formulate your ideas in an array language becomes important, because at that stage, your advantage might be between the ears, not the machine. The fact that you can think about a problem in a number of different ways, come up with a number of different solutions, bounce it off the machine, say, oh, that's the quickest one. You might be able to find that quicker than a person who's been used to programming in a non-array language.
Yeah, well, and one of the really big advantages of high performance, for what you can do, array programming, is that when you write that high performance code, it's not that far off from just straightforward normal APL. Maybe once or twice you'll use a workaround for a certain primitive that would get the job done better, but just isn't fast enough. But basically you're writing APL, and then you can rearrange and reorganize that as APL, and you can read it and get a much better understanding. And so you're not, if you try to simplify your code and improve your ways of doing things or add features or adapt it to stuff, you have a good programming experience with that, as opposed to if you're writing this high performance C with all these, like nested loops and fancy blocking things and branchless algorithms and all that stuff. Then you'd be wading through that because your details of how you perform well on the machine are mixed with the details of just what you're trying to do. And the APL, you're able to mostly just write what you want to do in this particular array programming style. And then it's fast. And that's all.
And I guess I'll ask a question of Conor. In case of C++, wouldn't the typical C++ programmer be in the same situation? They're not trying to write that ultra, or they're not trying to create those standard libraries and things. They're trying to use them and just put the code together.
I mean, it's a mix. I think most C++ developers aren't doing things with like custom allocators, and they're just using what the standard library provides you, or even if it's not the standard library, Google has Abseil, Facebook has Folly, Bloomberg has the Bloomberg standard library. And there's all these massive companies with performance, I wouldn't say critical, but like sensitive applications. And most folks aren't writing those libraries, they're consuming them. So I think you're correct in stating that. But that doesn't mean that there aren't the library developers, whether that's the standard library or the folks working on Abseil at Google, Folly at Facebook, etc. So I think, in most cases, people are using very performant things. I think similar to, languages like Rust as well. Rust has a huge crates ecosystem, and, they're making use of the iterator trait or the iter tools extension to the iterator trait, and they're just consuming that stuff. They're not actually implementing it themselves. But there's definitely a mix. I don't know what the percentage is. It's probably 90-10 or something like that. Something close to the Pareto principle, where most developers are consuming the libraries and there's only a small handful that are actually implementing them. But yeah, it's definitely not like comparable to the array languages, and where you're always just consuming. You're never writing a custom allocator in APL and then modifying the way that your reduction works on some kind of container. You're definitely not doing that. We're 15 minutes past the hour, as per usual. I have stayed true to my pre-show agreement of not saying anything inflammatory. At least I think so. But now for the listener that has stuck around for the full 75 minutes, I shall say the most inflammatory thing I can say without getting in trouble, which is that based on my profiling of the languages we're allowed to talk about, aka APL, BQN, and J, I assert that BQN is the fastest. Marshall, we're already over time. You have 2 minutes to explain why. Go. Or deny the claim if you wish to.
Just link to the page on your BQN website. Link in the show notes. So it discusses all about performance.
Well, I mean, yeah, there's a BQN page about performance that I think Rich is right that I should refer to that for anybody who wants real information. And for anyone who really wants real information, you should just go to bench array and see the graphs of how fast each primitive is that tries to explain, what performance you'll see.
Bench array? Wait a second. What is bench? I know we haven't brought this up. There's benchmarksgame.com or something, which is the website that like compares all the different languages based on a few programs. This is clearly not. What is bench array? Is that a BQN thing?
Yeah, pretty much. So bench array is my effort to benchmark stuff in BQN, mostly so that we have guidance when we're developing it. But I've also tried to present there's a page that it links to where I try to present these benchmarks along with some information about, what you can expect from the primitives. So it shows, like if you're sorting a 2-byte array, here's how the performance, here's what the number of nanoseconds per element it takes on my particular CPU that I benchmarked on, and it explains, here's what we do. And so here's why you see this little bump here or whatever. And so that's if you really want to get into BQN performance seriously. I mean, of course, you should always write your own benchmarks, time your own program. It's like, the majority, it's hard to say how much, but a huge amount of the time, you'll find that the thing that you thought was slow and tried to optimize, if you didn't benchmark in advance, is not actually the bottleneck, and it doesn't matter at all. And there's some other part of your program that you need to be focusing on. So, I mean, the number one rule of performance is benchmark everything, measure, as much as you can. But if you want to learn like general rules about BQN performance, you can look at this and see, how fast the primitives perform, and then have an idea of, which primitive you want to use more and which you don't want to use as much.
Unfortunately, your 2 minutes is up, and we didn't answer the question at all. I'm just kidding. Go ahead.
Yeah, so that's if you want, to stop being to get away from the drama and actually figure out how to make your program fast. But for the drama, yes, I do think BQN has some advantages even in the language design itself over APL and J. There are also some design decisions in APL and J that I think are holding them back in performance somewhat. One in APL that's kind of interesting is actually that all the bits in a packed bit array, regardless of the system you're on, they're stored big Endian, which is the opposite of the way that Intel processors and most that x86 and ARM and other processors these days do it. At the time, it was kind of a mix of both, and they chose to go with big Endian. But this means that some things have to be flipped around, and it slows them down. One of the big things I see with J that's really hurting performance is that it doesn't optimize as much in terms of the types it uses to represent things. So I said a big advantage of APL is that you can store things in bits or 1-byte integers or 2-byte integers. J pretty much just stores its integers as 64-bit integers, which is very large. And of course, the floats are 64-bit floats. You can't really do much about that because you can't lose precision. So there's no smaller format that works. But with the integers, that's a significant problem for the kind of code that I work with. Because, I'd be seeing 1 and 2-byte integers, like a lot of stuff like compiling BQN. A lot of programs that I write are BQN related. So yeah, for the problems I see, BQN is going to get that 8 times speed up from storing it in 1 byte or 4 times from storing it in 2 bytes. That's not necessarily always the case because other people work with floats a lot. And then for them, J is great because they get, double precision at the speed that the CPU can do it. And I think this is must be a lot of J's user base because they're I know they're very concerned with optimizing their floating point performance. Like their matrix multiplies are better than any other array language, I believe. They've done a lot of work on that. Good stuff. And things like that. So actually for some scientific applications, J is probably really good. So it depends on what you measure a bit. But also, I think BQN has some good stuff that it does, and we have worked a lot on our algorithms, of course. So I was not terribly surprised to see your measurement that APL or that BQN is faster than APL and J here, because like I've also used bench array. There's a mode you can use that I don't publish because I don't want to keep track of what changes are in APL and J right now. But I can compare against J and APL timings, and for the stuff that we measure on bench array. BQN is quite often a lot faster, twice as fast as dialogue, and a few times faster than J. It depends on the type a lot.
One of the key things I hear you talking about is the fact that you have bench array and you have a way of breaking down. For somebody who is really interested in being performant, you're basically giving them the keys to say, this is how it works, this is why it's fast, this is where its hitches are.
Hopefully. I mean, there's one of the things is that there's always so much more detail that that's affecting, like certain edge cases or things like that. So it's really hard to know, how exactly the primitive performs.
But in the case of J, I think what Henry has to resort to, I mean, he can give some really good explanations about how it's working and everything. But there are times where he just says, here's the source code. Take a look at it because you're gonna know as much as I might about certain areas of this.
And there are absolutely things where I can write them, but I can't say, how they'd always perform. I don't know if there are bad cases. And this is with, more complicated primitives like the interval index or bins is what BQN calls it. Not like, all right, so we do know how addition performs. We do know those things, but more complicated primitives, there are a whole lot of algorithms that you can apply. Some are better in, certain cases that I don't think of as important, but I don't know if people really rely on those cases. I mean, so what I try to do is, lean to stuff that has predictable performance that one of the big factors is it's not going to depend a lot on CPU branch prediction. So it works as quickly on, random data that the CPU can't predict as on regular data that it can. And I mean, maybe your data is regular and a branchy algorithm would be better, but it's hard to say. I mean, I try to lean to stuff that's more predictable that I can tell, a story that is understandable about what the performance is.
Well, I think that was fantastic, and I'm glad I asked it. I hope most listeners stay tuned. I mean, the ones that gave up at some point are not listening anymore, but I mean... Probably
somewhere around the music analogies, I'm guessing.
I mean, maybe we should make the cold open. All right, now I'm going to say my inflammatory thing so that people will hang on until they...
And then they know it's coming, yeah.
Yeah, they'll know that it's... or maybe that's what we should do. We should always make whenever we're not sure people will listen the whole thing, just put a fake cold open. And no, just put a fake one there so they're like, oh, when's it coming? And
then we guarantee they listen the entire time waiting for it.
Yeah. And they're like, well, I was waiting the whole time.
When I'm editing, sometimes I think that. I wonder if I put something in nobody's ever going to hear. What would they do?
We got this far. We haven't actually talked about like how do you actually run your expression timings in any of these languages.
Oh yeah. We can do. I mean, I was gonna rattle those off super quickly because it's super easy. We'll link something in the show notes. But for BQN, it's using a system function called _timed. For J, it's using a form function, I think it's called, which is 6!2, which in most examples people just assign to a function named time. In APL, it's bracket runtime, which you can specify a parameter -repeat equals the number of times. And there's also other ones in APL like compare x.
That runtime is a wrapper over CMPX.
Okay. And note that you have to load defuns, which is right parentheses, load space, dfns in order to get access to that. And then in Q, it's /ts. And then if you want to add a colon plus a number, that'll repeat the number of times. And depending on which language you're in, be careful because they multiply they don't do the division of like the number of times you ran. So if you do something, it's like, how is this 100 times slower? You might actually have to do that division manually. What were you going to say, Marshall?
Yeah, Q is the tricky one because it's total time in milliseconds. So yeah, watch out for that.
And if you do get in Q, you can measure it, but you can't tell anybody.
Oh, but you can measure NGNK, which is...
Yep, and John N is okay. Whereas NGN, I guess he was not performance concerned.
No, NGNK has decent performance.
NGN is more decent performance. Okay, it was not bothered, right? Yeah.
Yeah, because it's written in JavaScript. So.
Well, I guess maybe the last thing we'll say is if you have feedback on this episode, because I think, I don't know how we would break it up, but like the first maybe 75% was a bit more philosophical. There was a couple technical bits here and there, but really not until the end were we talking more about like implementation details. We have no idea what the listener enjoys or wants to hear more of. We talked about, maybe doing a part 2 or part 3. If you are interested in hearing extended versions of certain parts of this podcast, please reach out to, I guess we can throw it to Bob. You can reach out to us at
contact@arraycast.com. That's where we end. And I'll just also get a shout out while I can for Sanjay and Igor, who provide the transcripts for these episodes, which are often the way people consume them.
Yeah. And I think at least I personally am interested in the feedback people have listening to this stuff, because I'm sure we have a certain category of listeners that could care less about perf and they want to hear more about the notation as a tool of thought topics. But
they're the wise ones.
But there might be another category of folks that are really interested. I think it would be great to have another one of these conversations, whether it's more technical in nature or not, when Steven's back, or even not Steven, but some like a representative from KX that is able to say up to a limit of, what they're able to say. And, I'd be interested in that conversation, whether the listeners would be or not. We will only find out if you let us know. So
release the K tapes. Release the...
Yeah, we want the Snyder cut. All right. I guess with that, we'll say thanks for listening and happy array programming.
Happy array programming.